physics, historic breakthroughs can often feel underwhelming for those not familiar with physics. In fact, they may not even feel like breakthroughs sometimes, given that they get mired in very complex and abstruse calculations and equations. What an experiment known as G-2 at the iconic Fermilab in Batavia near Chicago has produced can also fit that category. However, for those who practice physics, the findings reached after firing a subatomic particle known as the muon through a 14-meter ring and then subjecting it to a magnetic field suggest that we could be witnessing the emergence of either a new subatomic particle or, more thrilling, a new force, a fifth force. Some of you may know about the four fundamental forces of nature: the gravitational force, the electromagnetic force, the strong force, and the weak force. If the muon G-2 experiment rises to the significance of 5 sigma in the next couple of years, we could indeed be witnessing the discovery of a fifth force. For now, though, there is a 1 in 40,000 chance that the result could be a fluke, which gives it a statistical confidence of 4.1 sigma, which is good but not conclusive. 5 sigma, or 1 in 3.5 million chance of the observation being a coincidence, is the gold standard to claim a breakthrough. Muon Reports has that story. In June 2020, some 170 international scientists made rather complex calculations and arrived at this number. The number, known as the G factor, is hugely significant since it holds within it the promise to redefine physics by locating a potential new force of nature. So far we know of 4 forces of nature: gravitational force, electromagnetic force, strong force, and weak force. If the results of what is known as the G-2 experiment, spearheaded by the iconic Fermilab in Batavia near Chicago, are any indication, scientists should be on the verge of finding that fifth force. The calculations have greatly excited physicists who believe this could be one of the most defining breakthroughs in particle physics since muons, the particle known as electrons' fat cousins, in the experiments displayed a strange disobedience of the laws of physics as laid down in the Standard Model. It finally proved this experiment could be even more significant than the much heralded 2012 discovery of the Higgs boson, a particle that lends mass to other particles. Muon Reports this weekend tells the story of the likely emergence of a fifth force of nature. Albert Einstein famously said, in reference to the deeply baffling universe, "Subtle is the Lord, but malicious he is not." He explained what he meant by that, saying, "Nature hides her secret because of her essential loftiness, but not by ruse. Nowhere is nature's subtlety more evident than at the subatomic particle level. One such elementary particle is muon, which is one of the 17 fundamental particles that constitute the Standard Model of elementary particles. Muon is known as a fat cousin of electron because it is 200 times heavier than that."
So a muon can be thought of as a heavier cousin of an electron. It's about 200 times more massive, and it has many of the same properties that an electron has. Except that because it's heavier, it can also decay, and in general it takes about 2 microseconds and then it decays into an electron.
Most importantly, muons are electrically charged particles with a property called spin. As a result, they behave as if they have internal magnets.
So a muon has this quantity which effectively means that if you put it in a magnetic field, it spins around just exactly like a spinning top. And the G factor, this G number that we're trying to measure, directly relates the strength of the magnetic field to the spin of the muon and tells you how quickly the muon will spin when it's in that magnetic field. So the G factor causes the muon spin to wobble when you put it inside a magnetic field.
Scientific theories initially predicted that the muon should have a G factor equal to exactly 2. But it wasn't so simple.
So in general, you might think that the vacuum itself, if you just have a vacuum chamber with nothing in it, there's nothing there. But in reality, due to something called the uncertainty principle, we have particles that come in and out of existence for just a blip. And so they come in and then they vanish again, and then they appear and vanish again. And so as our muons are going around, they're not only interacting with the magnetic field, but they're also interacting with these virtual particles, which come in and out of existence.
I like to think of it a bit like when you put too many pieces of paper behind a fridge magnet. If you add an extra one in there, it doesn't feel the force as much and it will fall off your fridge. The muon's going to just slightly, for a tiny amount of time, feel a slightly different amount of force depending which virtual particle got in the way.
In June 2020, some 170 international scientists made rather complex calculations and arrived at this number. The number known as the G factor is hugely significant since it holds within it the promise to redefine physics by locating a potential new force of nature.
The more precisely we can measure the speed, the more sensitive we are to learning about different types of these virtual particles. And the hope is that eventually, if we measured it really, really precisely, we might be sensitive to new particles from beyond the standard model that no one's measured yet.
That's where Fermilab's Muon G-2 experiment comes in.
The Muon G-2 experiment involves taking muons and we put them inside a big magnet where we store them and send them around and around. And while they're in there, we measure the frequency at which their spin rotates within the magnetic field. So we can measure this quantity very precisely, and it can also be predicted very precisely. And the main goal of the experiment is to make the measurement and compare with the theory. And if they disagree, then it's telling us that there's something in nature which is not in the theory. So the thing in nature is affecting the measured value and making it different from the theory, which doesn't contain this new physics. So this experiment builds on a previous experiment that ran at Brookhaven National Laboratory around the 2000 mark. It's a very similar experiment, actually using the same magnet to store the muons.
It's a C-shaped magnet, which is 7 meters in radius, and the unique feature of the magnet is how well shimmied it is, how uniform the magnetic field of the magnet is. So it's not only a big yoke of steel, there are many small shims, small parts we can use to tune the field to high uniformity.
So the Brookhaven experiment measured exactly the same thing that we're trying to measure in the Fermilab experiment. And the reason that we're doing it again is because it produced this really exciting result. And the reason it was so exciting is that it was quite significantly different from the standard model prediction. And nobody was expecting it, and no one really had a good explanation for why. But it wasn't enough different to call it a discovery of something new. For it to be called a discovery, the gap between the theory and the experiment has to be really more precisely known. So the theory community worked on reducing their error bars, and for the experiment side, we need to repeat the experiment with much higher statistics in order to reduce the error bar.
Improvements in the particle beam, experimental equipment, and methods allow researchers to make a measurement 4 times more precise than the original Brookhaven experiment. The new measurement has an extremely high level of precision, the equivalent of measuring the length of a football field with an uncertainty smaller than the width of a human hair.
It's just ridiculously precise. We're all going to be super proud that we managed to measure this precise number.
Now, after 4 years of assembling and calibrating the magnet, and more than a year of data collection and analysis, the Muon G-2 collaboration has its first result.
The unblinding was an incredible moment for the team. We finally agreed the analysis was complete and we had to, what we call, open the envelope, where the secret decipher code is. So that number then got typed into a computer with nearly 200 people watching in a special Zoom meeting. Whoa!
Wow!
Wow. Congratulations! Congratulations.
The new result does not agree with the standard model prediction, but it does agree with the previous experiment published almost 20 years ago. You can see the standard model on the left side, and you see the new average of the experiments on the right side. And there's a big gap of white space between them. As the gap gets bigger, this is what we mean by the significance. Many people ask whether we have really discovered something, but in our field, we like to set the bar of the significance of a new result pretty high, higher than most people might say. If you think about this in terms of a football field and you're trying to score a touchdown, we're in the red zone right now. We're in the red zone, and we need a little bit more data to either push it over, but you never know if the defense is going to come along, that being the standard model, and just kick us back. So we're sort of close, but not quite there. This is outstanding confirmation of experimental technique and very, very suggestive of the possibility of new physics. That's what we're after. That's the game.
Like he said, the result is not quite the final evidence of a fifth force, but it is very close to it. Fermilab has plans to carry out 5 more runs in the next year and a half. The goal is to establish whether the muon wobbling is commensurate with the standard model or is a harbinger of a whole new physics that factors in a fifth force. It's not yet fully clear what is causing the wobbling.
Since we use the subatomic particle called the muon, I thought it'd be good to first explain to everybody a little bit about what a muon actually is. So you can see this tableau on the left. Those are all the fundamental particles we know about in nature. They're the most basic ingredients. They're more fundamental even than the periodic table of elements. And the muon is one of those constituents. It's a basic ingredient in the recipe of the universe. It's very much like an electron. That's why you can see it. It's cast in this table down in the lower left, where it's right next to the electron, the normal electrons you would find circulating around an atom. It's similar in the sense that it has the same electrical charge and it has the same spin properties. You can kind of think of electrons and muons as little spinning tops. It has some important differences. First of all, they're 200 times more massive, which allows us to use them as probes to search for new physics in some ways more readily than the electron. And they're unstable. They only live for 2 millionths of a second. So once you make one, you don't get very long to work with it and run your experiments with it. That's also why we depend on a particle accelerator at Fermilab. You just can't go out and scoop up a clump of dirt and find muons in it because they will have already decayed. They are raining down on us naturally all the time from cosmic ray interactions, but we make very intense sources of them at the laboratory. So these muons, much like electrons, they generate their own little magnetic field because they have charge and they have spin. You can basically think of them as little bar magnets, spinning about, making their magnetic field. We're very interested in this experiment in determining exactly how strong that internal magnetic field is that's generated by the muons. It turns out you can determine exactly how strong they are by taking muons and putting them inside a magnetic field where they undergo a motion very analogous to the gyroscope you see in the picture on the lower right. So if you've ever played with these, a gyroscope has an axis that it spins about. And if you set it on a tabletop and give it a little push, that whole spinning axis will rotate, about the gravitational field you can't see that keeps it in the upright position. That's very similar to what happens to particles with spin like the muon when you put them in a magnetic field. They'll rotate just like that, and we call that precession. And the frequency that they rotate about is really determined by two things: the strength of that little internal magnet that we're trying to determine, and the strength of that external field that you put them in. So basically, by watching the rate that they revolve around and around, that's how we determine how strong that internal magnet is. We're particularly interested in that, and we define a quantity called the G factor, which is just a coefficient out front that tells you how strong the magnetic field generated by that muon really is. It's interesting. It's had a long history. You know, at the turn of the last century, classical physicists would have thought that the G factor should be 1. You should be able to determine the strength of that magnet, and that scaling factor G should just turn out to be 1. However, with the advent of relativistic quantum mechanics, sort of in the 1930s, it became clear that the expectation theoretically was 2. But as you might guess from the name of the experiment, there's a little more to the story. That's why we're called muon G minus 2, because we look at the part that differs in that G factor from being the perfect 2. So, and the reason that's interesting and the reason G isn't identically 2 is because the muon, like other particles, is never really alone in the universe. It's constantly surrounded by an entourage of other particles that fluctuate in and out of existence. They don't exist before. It's not like they're lurking under the covers. They really pop into existence and then they disappear just as quickly as they came. Oftentimes you'll see that referred to as quantum foam. And so this shows a picture of sort of what that looks like, with the muon spinning, processing, particles appearing all the time, and an external magnetic field overlaid. So the reason this is interesting is because you can calculate very precisely what that rotation rate should be based on all the particles we know about. So if you go out and run an experiment and you determine that rotation rate and you compare it to what we expect, the question is, do you get the same answer? Because not only do the particles we know about contribute to this, but it also has the potential for the ones we don't know about to contribute. Those particles can come from any one number of very big questions that we're trying to understand about the universe. For instance, we look out in the universe right now and we see roughly 4 or 5 times the matter that we would expect based on what's visible to us. We don't really understand. We think we might be swimming in a sea of background particles all the time that just haven't been directly discovered. Those are the kind of things that can appear and affect that rotation rate. Or, you know, there's other more sophisticated theories like supersymmetry that try to explain facts like, why was the Higgs mass when it was discovered so light? And of course, as an experimentalist, what I'm interested in is anything that might change that number, because there might be monsters we haven't yet imagined that are emerging from the vacuum, interacting with our muons, and this gives us a window into seeing them. And so the story gets particularly interesting because about 20 years ago, this experiment was performed at Brookhaven National Laboratory. And actually at Brookhaven, they found a hint that there might be new particles, new forces contributing to this rotation rate of muons in the magnetic field. You can see on this plot, what I'm plotting here is a quantity we call the anomalous magnetic moment. It's the part of that G factor that differs from 2, the interesting part, that only depends on all the particles that are fluctuating in and out of existence. And you can see by the purple band, this was the experimental determination from Brookhaven 20 years ago compared to the standard model theory as it's been calculated through today. And you can see there's a significantly large white space in between them. In fact, you know, this difference has grown over the years to become what we call in particle physics a sort of 3 sigma level result, meaning you would only expect this much white space about 3 out of 1,000 times you ran the experiment. So it starts to get unlikely. And in fact, that significance has even grown with improvements of the theory to a 3.7 sigma discrepant result. So this difference has been intriguing for physicists for many years to understand, you know, have we started to see a hint of new physics emerging in this measurement?
What is causing the excitement is the anticipation that the scientific community could be witnessing the beginning of a new physics. During a press briefing, one of the team members was asked to question whether it was indeed the case.
Okay, thank you. That is a really good question. So just going back to what we've already said, in terms of likelihood of new physics, we can quantify that for each of these results separately. And results that were recently announced from the LHCb experiment at CERN aren't quite at the same significance level. And what is really exciting about those results is that with more statistics, with more experimental data, the significance of the tension for these lepton universality violating ratios has increased rather than decreased. And that has all of us really perking up our ears and considering the effects of new physics. So the muon G minus 2 tension is larger, and we've already heard the numbers for the likelihood that going away, which is exceedingly small. But we really need to wait until we reach 5 sigma. So if we are in the place in a few years where both the standard model prediction and the experimental results stay where they are with errors reduced, we will certainly be able to claim discovery of new physics from muon G minus 2 alone.
Chris, this next question is for you, and it's related somewhat to what Graziano was talking a bit about earlier. This is from Frank Rodeluschen from German National Radio. When do you hope to reach 5 sigma, and are there other experiments planned to confirm this result?
Good question. Good question. So as Graziano mentioned, we're expecting to cut the experimental error bar in half in of order a year from now. It could be sort of on the time scale of not this summer, but the following summer that will release our next result. So we're anxious to see what happens to the theoretical value over that same time, because as Aida said, there'll be some renewed interest in understanding all the details. That result has the potential to cross into 5 sigma. If the experimental values stayed the same, the theoretical values stayed the same, we could be looking at 5 sigma discovery threshold, by a year from this summer. And then when we have the additional factor 2 reduction error, then that will take yet a couple of more years, because we're still taking that data sample and it's yet to be analyzed. So that's kind of the time scale.
At that level of physics, everything is too subtle and hence may seem elusive. But the expectation is that in the next 3 years or so, we could be seeing a dramatic break from the standard model of particles. Thank you for watching Mayank Chaya Reports. We will see you next week again.